Haozhi's PhD thesis presentation. So Haozhi is jointly advised by Professor Yi Ma and myself. And this is kind of a wonderful occasion when a student finishes a PhD, but also slightly sad because it is, from the perspective of an advisor, it is like when a child leaves home, you know. So you expect them to leave home, but you are sad nevertheless. So Haozhi came to Berkeley with a strong background in computer vision. He had done this work on deformable convolution, which was very important and influential in object recognition. And then here, like a few others of my students, he made the journey from computer vision to robotics. In particular, he has done a lot of work in robotics on dexterous manipulation, which is multi-fingered hands with tactile sensing. And here I want to acknowledge collaboration with Roberto Carandra, who is in the room. And he's going to tell us all the wonderful results that he has obtained. Yi, would you like to add something? That's, as a co-advisor, I want to give Yi also an opportunity to add something.
Can you guys hear me?
Yes, yes.
Yeah, thanks, Jitendra.
So yeah, as I agree with Jitendra, and I got to know Haozhi from colleagues in Microsoft Research Asia, and came to Berkeley, and really actually, first I had a little bit doubt that he's actually got into the robotics background. He doesn't really have, he didn't have the background, but he actually got into it with very strong self-learning capabilities and a passion, I would say, dedication. Yeah, it's been a very, great pleasure working with him through the last few years. Yeah. Again, yeah, without any further ado, I'll probably let him to get to his talk.
Great. Thank you for the kind introduction. I'm Haozhi. Today, I'm very excited to be here, and also at this special occasion of the last day of the semester and the next day of NeurIPS deadline. And also present my work on, my PhD work on multisensory dexterity for robotics. I guess the motivation of this, or I guess every people in this room would love to have a robot in their home. The robot should be able to handle every chores from cooking and then laundries, so that while they are doing the work and we can enjoy our life. And nowadays, we do have a lot of useful robots in industrial settings, such as car factories and warehouses. They are extremely successful at performing certain tasks. They can lift heavy objects beyond human capabilities.
Some audience says, like, can you share your grade?
Oh,
Yeah.
really? Okay. I'm sorry about that. I think it's oh, it's good now? Okay. Let me just say, these are extremely successful examples. They can assemble or transport things just faster and with greater speed than human. But meanwhile, there are specialized machines at some specialized tasks. If we want to transfer these same techniques to unstructured environments, things will get a lot more challenging. Imagine building a robot prepared breakfast for us. This is probably what will happen. And although this example might be just a funny example of trying to show robot failure, but it really shows there are a lot of challenges before we moving the robots into our unstructured environments, such as our homes. And among all the challenges you can imagine, either from vision, machine learning, or plannings, my research focuses on solving two particular challenges. The first one is, instead of trying to use specialized end effectors, such as grippers or suction cups, I'm trying to see how can we give robots the ability to use multi-fingered hands and build robot dexterity, which means the ability to control and coordinate multiple degree freedoms to achieve a desired object movement. The second challenge is, instead of using simple sensors, how can we enable robot using multisensory AI, specifically the integration of vision, proprioception, and tactile sensing? I think these two challenges are pretty fundamental for bringing robots into our home. And to illustrate why, imagine today is not 2025, but maybe 2030, then what will have changed? Of course, by then, if you are a PhD student right now, you will hopefully have graduated. But another thing you can imagine is that given the rate of AI progress, we have a new model every weeks, then maybe by then we have already achieved human level AI, at least especially in perception, planning. Then what would happen if we put those AI systems into robots we have today? And of course, we do not have such AI system yet, but there are still something we could do. Here's a video in which I directly control a pair of grippers to perform, this is one popular choice of specialized and effectors, to perform a simple task, just cutting this apple. Now the point is the perception and planning are all human level because I'm the operator and I obviously have human level intelligence. But you can see it's not easy at all. Picking up the knife is challenging. Cutting the apple is even more challenging. I also tried a lot of different ways, but none of them is successful. But in contrast, we can easily do this without any problems because these tools are designed for us. We have multiple sensory informations, in this case, especially vision, tactile sensings, to help us make decisions and executions. So I believe that if we want to build this intelligent robot that works in our homes, help us with tasks we are interested in, they need to interact with objects we are interact with, and therefore they must be equipped with multi-finger hand and multisensory AI. And then with this goal, I will present my work on the intersection between these two areas. I will start by presenting this scalable framework for developing robot dexterity using proprioceptions, a very simple yet very powerful sensing. And we study how to build robot dexterity and study how to control and coordinate multiple degree freedoms to achieve desired object movement with 3 examples. First, we study in-hand manipulation and develop the ingredients for generalizable policy learning. And then I will very briefly talk about 2 extensions. The first one is extended to more complex systems such as bimanual manipulations. And the second is extension to more dynamic tasks such as spinning a pen-like object. In all of the experiments, we not only achieve great performance on a single object, but also we focus on the generalization capabilities across different objects, as shown in these videos. I will then show my work on combining dexterity learning and multisensory AI, and to enable examples, including to enable more complex manipulation tasks, such as in-hand object rotations over arbitrary axes, and using vision and touch to learn the shape reconstructions during manipulation. And I'll start from how we can build generalizable dexterity using proprioceptions and actions. A little bit background in this talk, when we say proprioception, it specifically refers to the robot's current joint positions. All the robot I'll show today can be viewed through the following abstractions. On the left is a real multi-finger hand we are going to use. In the middle is the kinematic structures, where it has 4 fingers, and each of the fingers can be seen as some rigid link connected by rotational joints. So the joint angles theta 1 to 3 here is what we used as the proprioception. The hand we use has 16 fully actuated joints, and action simply means the policies commands that specify the target joint actions in the next time step. And I will illustrate our methodology using in-hand manipulation as an example. We chose this task for 2 reasons. The first one is a fundamental part of how we interact with the world. One example, like when I'm doing this cutting an apple examples. The way I pick this knife is different from how I actually use that. I need to reposition this knife in my hand to actually perform this cutting. Other examples also including hammers, hammer and nail, as well as directly using fingers to installing the light bulb. So this is so easy and intuitive for human, but for robotics, it remains very challenging for many years because it involves frequent changes in the type of contact you make between the manipulators and the objects. You kind of need to grasp objects and then re-grasp it after breaking the contact. And then all this makes it very challenging. And over the past at least 40 years, there are numerous roboticists trying to study these problems. But it also makes it a very, it also makes it as an excellent testbed for evaluating our algorithms. And over all the past work, despite we already have a very good controllers for probably one or a few objects, but the key bottleneck here lies in the capability of generalization across different objects. And in contrast, my work aims to build a policy that can generalize to diverse objects in the first place. And I would like to show you the result first. The task here is that we hand over an object to the robots, and the neural network is trying to send commands to the robot to control the hardware to rotate the objects over the z-axis, similar to a human installing a light bulb. And if we look closer to the results, the policy is able to generalize across objects with different physical properties, such as it can manipulate objects with different weight, different coefficient of frictions, different center of mass, as well as different shapes. Yeah. And then I'll use this work to explain what are the ingredients of what is the ingredients for achieving such generalization capabilities. First, our control policy is a neural network trained with reinforcement learning. Then the first question is, where does the data come from? We use large-scale parallel simulations as our data engine. It contains thousands of robots simultaneously interacting with the environment and collecting data. And as a result, it can generate data tens of thousands times faster than the real-world data collection systems. And each of the robots is interact with objects with randomized physical properties. And by learning with all these randomized physical properties, and so after the policy is able to dealing with all of them, it should be able to work directly in the real world when we given it a new objects. Then the next question is, given that we have already a lot of data from randomized physical properties of different objects, what will be an expressive class of functions to learn that policy? In typical reinforcement learning, the control policy is something like this. It takes some observations, it outputs some actions. While this performs very well for many of the tasks, in our case, it does not consider the difference between different objects. And therefore, we choose to use physical properties as an additional encoder or additional conditions into this policy to make the reinforcement learning algorithms aware of the difference between different objects. And to implement this idea, we can get the ground truth physical parameters from the simulator and feed it into an encoder. The result object feature, ZT here, will be fed into the control policy. And the physical parameter here specifically means object 3D positions, object mass, center of mass, coefficient of frictions. We can jointly optimize the control policy and the encoders using just the standard reinforcement learning algorithms. And the rewards contains several equations, but what is important is that it is actually, one of them is trying to maximize the angular velocities of the objects. And the other components on the right is really trying to penalize the applied torque and the smoothness of the policy. Then with these conditions, physical parameters as conditions to the policy, as well as the large-scale physical simulations, the policy is very easy to train and perform very well in simulator. And the only problem remaining is that in the real world, we do not have these physical conditions anymore. Therefore, we need to have a sensory sequence to infer that properties, which is the third question: what are the right sensory inputs? And in this work, we find that proprioception and action sequence can infer object features. And allow me 1 minute. I will first assume this statement is true and explain the training paradigm, and then I will explain why this proprioception sequence can infer the object features. So imagine this statement is true, and we can have a proprioception action sequence to infer these object features. We are going to have a randomly initialized predictors and trying to make predictions of these object features. In simulation, we can generate a huge amount of data. And at each time step, we are going to train this predictor by minimizing the gap between the ground truth object features and the predicted object features. And after training long enough in the simulation, this gap is small enough so that as long as we directly copy the control policies we trained previously and use the predict feature as the input, it should work well in the simulation. And now, because all the sensory motor sequence is readily available in the simulator, in the real world provided by the hardware, so we can directly deploy the bottom policy in the real world. And this policy is what we use to produce the demos you see in the previous slides. And now we have all these three ingredients. Of course, I owe you an explanation of why this sequence can infer object properties. And it sounds also surprising to me in the beginning, but let me go back to this very simple example, a robot hand trying to rotate this tennis ball. And I'm going to illustrate how does it making predictions of 3D positions using one of the joint as examples. The joint we care about is the bottom joint of the pinky fingers, shown in the blue arrows on the left. Then if we print the positions, the joint positions, and the neural network's command on the right, we will get this curve. The neural network will command blue curves, while the actual joint positions is the red curve. And you might notice that, and also one thing I should explain is that the bottom joint, the moving of the bottom joint controls the side movement of the pinky fingers. So it's just keep contact with objects and moving away, contact again, and moving away again. And in this curve, you might notice that there are two different patterns in this curve. In one of the regions, we have joint positions is almost equal to the actions. In some of the regions, joint positions are very different from the actions. And this is actually how the policy can infer where the object is. Because this difference between joint positions and actions is when the contact happens. For example, when the joint positions not equal to actions, then it corresponding to the pinky fingers is not in contact with the objects. So whatever the policy given command, the joint will moving to the desired positions. And for the green regions, it's actually corresponding to when the finger is in contact with the objects. And in those cases, the finger is in contact and applying force to the objects. And the policy takes a sequence of that information, and it basically knows at each time step what is the contact state of each of the fingers. And you can imagine it also takes all the history of state of 16 different fingers, so it is easily know what is the relative position between the objects and 4 fingers. Thus, it can give a rough sense of various objects during manipulation. And thanks to the simplicity of the sensings, as well as the robustness of our method, it can perform well in various conditions. So after releasing our code, the colleague from University of Bristol trying to directly deploy the policy on a very similar but not exactly same hardwares, and it can directly working in their case. We also been able to bring this to different places for real-world demos, such as in Coral, where we are trying to rotating this orange peel, which is surprisingly robust in this case, as well as in last year's HICRA, where we try to giving demos and audience are trying to put random things on the fingers such as these phone chargers, and it's surprisingly doing some decent job on manipulating these phone chargers. And our work has also inspired a large group of researchers studying this either algorithmic paradigm as well as the task itself. For example, there's something rotating cube, but also on the top right, it can also rotating while changing the wrist positions to make it really like resistant to the direction of gravity. And in summary, in this work, we have developed 3 components for generalizable policy learning for dexterous manipulation. And this will be the fundamental framework for the following projects and following talk. And another insight we get is about how should we design the training environment in physical simulation. And I think usually one of the challenges that prevent students from using simulator to train a policy is that building the training environments takes a lot of time and thus not very scalable. To get the objects or the scene models, we either need to rely on artists or camera scans or computer vision techniques to get that. And every time we trying to have some new tasks or new objects, then this will take some time and possibly from PhD's time. So the way we are going to do that is instead of trying to get accurate objects models, we are trying to mitigate this by creating an approximate asset that results in good policy. And what does that mean is consider this in-hand manipulation on these objects with holes on the surface as an example. So if we want to create an exact similar asset for these problems, we need to find a similar asset and model the concavities of the mesh, which each of them is very challenging or time-consuming at least. But in contrast, what we have done is using approximated asset for policy training. Specifically, in this case, we just use cylinders with different poses as the training set. Then why this works when the training and deployment scenarios is so different, or why using the approximated shapes makes sense in the first place? I think this is because the important thing in manipulation is how you make contact. And the contacts are very local events. So the policy only needs to take care of the contact events between the fingers and the objects, instead of consider the global geometries of the objects. And although there are really infinite variants of different objects in our real world, the type of contact, these contact properties, are inherently low-dimensional things, such as we either contact with a spherical surface or contact with the edges, which has already been covered when training with cylinders from different poses. And the idea of focusing on this local contact is really important to scaling to more complicated tasks. And unfortunately, because of the limited time, I might only able to show the teaser videos without going to technical details of each of the work. So we have studied how this idea of using approximate assets for manual manipulations, using twist leads off as examples. So using the same methodology, we can try to train 2 hands, twisting this leads off and generalize to different leads, as well as how we can use real-world data to augment and fine-tune this policy so that it can work for more complex and dynamic tasks, such as spinning these pen-like objects in the real world, which requires very dedicated dynamic balancing. And in the next part of the talk, I will show my work on using multisensory AI to enable better manipulation and perception. The first example I would like to show is more complex finger coordinations. So recall that in the previous work, we have built policies that is good at z-axis rotation. However, it fails when we want to extend it to more complex motions, such as rotating objects over the x-axis. X-axis here means like something motions like this. It's also what we call finger pivoting. And this fails because it can only, the previous approach can only infer rough locations of the objects. And when the manipulation requires more fine-grained sensings, it will have its problems. And we improved trying to improve this method by augmenting the inputs with vision and tactile sensing with vision and tactile information. And inspired by how human doing manipulations, where we continuously making multisensory predictions, as well as the tactile sensing by nature will give us more fine-grained details such as the type of contact, the local geometries of the objects. And the hardware setup is also quite simple. We have these RGBD cameras, third-person view cameras, providing the scene depth. And it looks at the objects on the hand. We also have 4 tactile sensors giving us tactile informations, each of them on the fingertips. And I'll talk a little bit more about the tactile sensors. It's a collaboration with Meta and Roberto here. So the sensory build is basically in the category of vision-based tactile sensors. The mechanism has a lot of other functionalities, but for this project, what is important to us is there is a camera in the middle of the sensors, and there's a few LED devices sending lights to the right, and there's a soft elastomers will reflect the light that will reflect the light and changing the reflection after deformation. Then the camera will capture such deformations so that the image will change when there is a contact from different directions. For example, when there is no contact, the camera will display a static image on the right. But when there is object contact with the fingers, the finger will deform as shown in the middle. And then the image will change accordingly to indicate there's a contact and where does the contact come from. And we trying to build this system following the same recipe we have before, because we want to still get the benefits of them. And the only thing we changed is changing the last component to incorporate sequence of multisensory information. Well, this provides a lot of benefits in theory, but it also brings new challenges because we are going to use vision, touch, and also simulators. One challenge is that simulating them is usually 10 or 100 times slower than simulating physics only. And because the actual effort we need to put on either physical rendering, rendering pixels, or the interaction between soft materials. It will also give challenges for larger sensory gaps between the simulation and the real world, given the limited technologies we have for simulation. So, and then we are going to have some ways to solve them one by one. For the first challenge, this is a problem because we want to have the benefit of using reinforcement learning so that we can learn very complex motions. But RL is really sample inefficient. So to solve this problem, we decompose it into 2 parts. We are going to training the inefficient reinforcement learning with sensors that can be simulated very fast. And then we are going to do supervised learning using for the sensors that are slow to simulate. Specifically, we train the data inefficient RL only using the state input, such as object positions, poses, robot pose, object shapes, represented just by the surface point clouds. They are very fast to generate. And in the second stage, we are trying to include vision and touch that is very slow to simulate as input, but instead using supervised learning to imitate the first stage output. Then, although the simulating vision and touch would be slow, but the learning becomes much more efficient. So the total work clock time is still within a reasonable range, such as a few hours of 10, maybe 20 hours to a day. And for the second challenge, the solution is trying to find some intermediate representations that to make the simulation and the real world gap smaller. For example, if we directly using RGB values to train our policy, the simulation and the real world gap is pretty large, such as on the left is the simulation pixels, on the right is pretty different in the real world pixels. But we're trying to use intermediate representations in this case to make the gap smaller. For example, for vision, we can use object depths because they all, in simulation and real world, they all follow the same projective geometries. And we can also compute the depths using object shapes and camera parameters easily in the simulation. And in the real world, we just get RGBD images together with segment anything to segment the object depths out. And for touch, simulating it is even more challenging because it involves a lot of interactions between soft materials, which is either very slow to simulate or not accurate in simulation. Then we choose to use a low-dimensional representation of touch, namely the 2D contact directions. More specifically, when the objects contact the fingers from different directions, the image response will behave differently. So for example, when the objects either contact from the back or from the right, so the images will change either to the left or to the bottom in the bottom row. So we can then use a very simple color tracking algorithm, such as just looking at the red blob, to measure the pixel displacement to get the direction of the contact. For example, in this case, we can get the direction of the right blob displacement on the top row as going to the bottom left. And on the right, on the bottom, it would be the direction of contact is to the bottom. And then we can discretize it to 2D planes to get more robustness in the real world. And this is how we process the touch information in the real world. In simulation, we can directly query these informations from a contact buffer and get matched results. Now we are going to using the same pipeline, but now having multisensory informations as the input and trying to predict the object feature. If we look at the same task before again, so now the policy is able to rotate objects with three principal axes, x, y, z directions. And one interesting phenomenon is that if we look closer to the thumb on the left examples, so sometimes the thumb needs to make one attempt to going from the bottom to the side, but sometimes it needs to make two consecutive attempts. So the difference between the strategy or the adaptivity of the strategy, meaning that the policy is able to have some fine-grained sensings of various objects and various fingers relative to objects to make the correct next step predictions. And here is another gallery of showing different objects we rotate different objects over different axes. And in summary, we have identified several problems when we're trying to incorporate vision and touch and solve them one by one by changing the training paradigm as well as changing how we represent vision and touch. And although I'm mainly showing only the in-hand manipulation examples, but other researchers also use it for insertions, grasping, or using different tools to showing the flexibility of the proposed methods. And in addition to this improving manipulation, we also showing multisensory informations can help perception. And in a recent work we published in Science Robotics, we are interested in, given an unseen object to the robot, how can the robot reconstruct its shape and track its pose? And similar to how humans manipulate novel objects in their hands to understand its shapes, we should be able to perform such explorations after we have these in-hand manipulation capabilities, such as playing the objects in hand or twirl the objects a little bit. And we approach this problem by using a combination of vision, touch, and proprioceptions, and incrementally build an object representations that can give reconstructions of its shape and simultaneously get the pose of the objects. And more specifically, given the sensory input from a third-person view camera, as well as full tactile sensors on the fingertips, we first having a perception module that gets object depths using the same method we use for the previous work by using segment anything, and also get the finger contact depths provided by the tactile sensors on the fingertip. We are then trying to now the insight we have is we are going to use the tactile sensors as a perspective RGBD cameras. So because we know the joint positions, so we know the relative positions between the fingers and the objects. And then what we really have is at each time step, we are going to have 5 different depth cameras. And this gives us an opportunity to formulate it as a multi-view reconstruction problems. So we can formulate the objects as the sign distance functions. And at each time step, we are trying to supervise these sign distance functions from 5 different sparse views. Initially, this can be very not accurate, but over the time, it can becomes more refined, and then gradually it gets more and more accurate. And finally, we can achieve these results of incrementally refinement of the object's shape. And this also applies not only for one object, but a lot of other different objects. And with that, I'll stop here. So that brings me to the end of the technical sections of my talk. And I want to say, before my acknowledgement, do you have any questions? I intentionally skip some of the results because I want to leave a lot more time for acknowledgement. Yeah. Yeah, but I want to answer the technical questions first at this stage.
Just now you mentioned the representation, so I'm wondering, do you guess the company? I also tried this with robotics before. If you want to get a good representation that's joined to both touch and vision, do you have any further idea, maybe to combine the touch vision language audio together?
Mm-hmm.
To learn different representation together.
I think maybe this is not my expertise, but I just having some guess. I think there are some cross-model predictions way that you can do that. So when you having multiple sensory informations, the unique advantage is that you can have complement informations between them. So sometimes when vision see 2 identical textures, but not textures, but maybe the colors, but their texture might be different, and you need to use touch to feel the difference. So this type of thing, if you can making a prediction of what is the signal you get from what is the signal you get using tactile sensors by combining audios, vision, and language. So that would be making the representations meaningful in terms of you can infer something vision alone cannot infer, but by adding more modalities, you can infer. So it's a kind of a self-supervised way to do that. Okay. There is indeed some questions in the Zoom. For me, a human to know what. Okay. I see. So I think it's not a technical question, but I think I'll go directly to the acknowledgement section. So the reason I want to leave more time for this is because I think probably many of you have seen the technical sections many times, so I don't want to make you feel very boring. And I also want to say, I feel the most interesting part is for the dissertation is always the acknowledgement section. At least for me, the motivation of me joining other people's dissertation is to see the acknowledgement. And I also want to say, this is not the official series part of dissertations. Okay, so it's not research style. Okay, I think I will definitely start by thank my advisors Jitendra and Yi, from whom I really learned a lot. So I think Jitendra has a gift of making predictions. One of our papers, we start the first sentence of the paper saying it's hard to make predictions by born. But I think Jitendra has a gift for doing that. So he always sees several steps in terms of research fields ahead. And usually predict where the field will converge. So I remember our first meeting in SDH when I doing the school visit. He was telling me the order of revolution in computer vision will happen in the following order: it's recognition, representation learning, and 3D vision, videos, and embodied AI. And at that time, I only work on recognition, and I do not see it as an obvious thing. I think many people does not see it as an obvious thing, but it turns out to be quite precise and after so many years. And he also predicts that the next breakthrough in robotics would be dexterous manipulation. I would say this has not yet achieved a consensus, but I myself firmly believe that, and I hope my work can serve as a foundation for this breakthrough. After maybe 5 years, you can recall my sentence. And what surprised me most is, I think, how much attention Jitendra gave for each of the students and their projects. I mean, given his seniorities. So this is something I never imagined before I came to Berkeley. In fact, during the last few years of my PhD, I think Jitendra come to lab more often than I was. Maybe it's a problem of me, but this really shows how approachable and whenever you have questions, you can seek him for Jitendra's help. And next, I also want to thank Yi. A very surprising fact is that I actually know Yi from high school, and the name of Yi. And it's actually even before I know what is computer science. This is reading from some Chinese newspapers or Chinese social medias. So it's really surprising and exciting when one night I receive an email from Yi asking for interviews. So I was very excited. By the way, at that time, most interviews is done by either Skype or Google Meet, but Yi just called me directly over phone. And I don't think the quality of the phone is good. So I almost think I failed the interview, but very luckily, I finally end up here. So over the years, I really learned quite a lot from Yi, especially his mathematical understandings to these practical problems. And also his perspective on low-dimensional structures of the world. Initially, I was quite skeptical of this philosophy, but now, honestly, I'm deeply influenced by it's deeply influential not only in my research, such as the low dimensionality of the contact events I just talked about, but also how I view this world and how I make new research directions. So working with Yi is just both intellectual and philosophical educations. And I also want to thank Peter and Roberto for serving at both my qualification and thesis committee. So Peter has always been amazing figures in robotics and AI. And initially, when I switched from vision to robotics, I learned many of the fundamental robotics knowledges from his class. And throughout all these transitions from vision to robotics, every time I have some new idea, and later I realized this is something already done by Peter's group. So it's really showing how broad and how different frontier he has done for robotics and robot learning. And for Roberto, I think it really changes my research career by doing these fair-bear collaborations. And I think all of the knowledge I know about tactile sensings and many of the knowledge I know about classical robotics is taught by Roberto. And we have read many papers together and also organized workshops. And I think all of them, I learned a lot from not only technical knowledge, but also all the communication skills from Roberto. And I want to thank a lot of people. I will go through one by one. So I want to thank Yichao. So thanks Yichao for teaching me how to write proper research code. So we haven't, so in the early 1 year of my PhD. So I think initially I was very sad because someone saying your code is so ugly and it's not functional. But over the years, I realized it's really a good thing. So we haven't had a chance to collaborate after he graduates, but I think all my GitHub repo is deeply influenced by Yichao, how to organize different files, and also trying to make no open GitHub issues by actively interacting with them. And also thank Chongyou for teaching me a lot of mathematics when we collaborate on this isometric neural network, and also as well as ski. So all these collaboration opportunities tells me I'm not good at mathematics and also I'm not good at ski, but it's also a fun experience. I also want to thank Xiaolong and Deepak when they are postdoc here. They teach me how to write write every aspect of paper from introduction to the conclusions, as well as how to decompose the large problems into smaller achievable ones. And I want to thank Ashish. One of the skeptical I initially have about robot learning is that I should say when I start my PhD, the popular thing in vision is those adversarial examples and robustness neural networks. And people are arguing that you can not ever get a policy works by training a neural network in the low-level controllers, because all these requirements of accuracies when you're doing robot control. But working with Ashish and seeing his quadruped working is the moment that I start to believe that machine learning methods is able to do that. And that also changes what I want to do afterwards. And this is, this is very important moment for me. And also thanks for Brent, especially thanks for him to writing a lot of papers by changing my non-native speaker style to the real fluent styles. One significant change for Brent, significant influence for Brent on me is that I start to use Figma after our collaborations. And now my paper uses Figma in every figure. And I also thank Sudo taught me about different optimization techniques, as well as another good engineering tactile sensors. And I also want to thank Toru, who actually brings the by-many manipulations as important pillars in my research. And before that, I never thought about doing by-many manipulations on use and multi-finger hand. So I also want to thank another set of great collaborators, Jessica, Jun, Ying, and Haichuan. So this is in my last set of projects. They are actually doing the hard work so that I can just write papers and then click the submit. I also want to thank Mike and Ting Fan, who actually fixed the hardware for me by doing my job in beta. So usually, if you see the chat history, it's usually, oh, Ting Fan, this is broken. Is it possible to fix that? And when I say, is it possible, I mean, can you fix that for me? But they are so nice to help us with that. And also Himanshu and Antonio, who really teach me the value of video human data that I was skeptical, but later on I was convinced that it's the next breakthrough in robotics. And also Yanren for helping me set up the technical things there, as well as help with the humanoid projects. And it's really unfortunate that I do not have time to go through each of my collaborators and friends, but I have wrote them properly in my thesis. So I would like to thank all my friends in Bayer, in Berkeley, and also my collaborators. And I think hopefully you can check out the acknowledgement section of my thesis to see our memory. And then I want to thank my staffs in Bayer and also the CS divisions, which honestly, without their help, I cannot graduate, of course, for a lot of which class I should take and which class I'm missing, and keep reminding me what is the next step you need to take. And then I want to thank my parents. So this photo is taken in early 2019. Almost the beginning of my PhD, and many things have changed. I mean, I also look different, but their love and support is really won't change. So the only thing won't change is their love and support, regardless of how much time it has been. And I mean, it's also interesting that they are not technical, but they ask me what are those ChatGPT and humanoid stuff is doing, and then it's a good practice to explain this concept to them and tell them not buy some of the stock and not believe in all these hypes. Yes, and I also want to thank my cats. So this is Katsan and Gina. So I have them since they are very little, and it's a really fun experience to watch them fighting or playing with each other while writing different code. So this is a very fun video. I just let it play. Yeah, this is happen most of the times when they are playing each other. And I think finally, I also want to thank my wife, Xinru Yang, so who is sitting there. It's really hard to put into words what she has done for me throughout this journey. So she was asking me, why you are still making your slides before your dissertation? And I was saying, it's very hard to say, just to organize it into words. And some interesting fact is that I published my first PhD paper after we met, and I published my first robotics paper after we started dating, and I published my first authored robotics papers after we got married. So, so she has stood by me through every important moments of my PhD, and her support and the belief in me carried me through every failures or depressions or burnouts. And none of the work I presented today would have been possible without her. And luckily, we have been many places all over the world and have great memories. But I also feel a little bit sorry in terms of every time during all those occasions, I need to bring my laptop along and and end up working some of the time. So especially this one is I just get back from this one last week, and then I was working on some dissertations. And thank you for always supporting me and for understanding what this journey has demanded. And the last slide is a photo from February 22, 2022. I think this is a very special date that you can yeah, all of these are twos because this means together. So it's the day we got married. It was the most exciting and meaningful moment of my life. So I think I'm always been someone who is afraid of many things. So I'm afraid of trying new research directions or missing deadlines or not being good enough in general. But through all these uncertainties, Xinru has always been on my side. She has been my calm and my courage. But she, I know, is not a fearless person. She also has her own fears. So the fear that that love can be fragile, and something so warm and beautiful today could disappear suddenly in one day. And I definitely understand that. So we also believe in the following quote, that no one is born good, but it's the rules and the restraints of civilizations that make people behave morally. And I think that's why I feel that I always owe her something. So although we have married for 3 years, I have always owed her a real proposal. So I want to use this moment to make a promise, not just in words, but in front of everyone that is important to my future career. And I want to ask again, formally, Xinru, will you marry me?
With no makeup. I look different from the person on the picture. But yes, always. I'll see you later.
Okay, with that, this is the end of my talk. It's a great timing.
You all know the bar has been set.